So my name is Miles Cranmer. I'm an assistant professor at the University of Cambridge. I work on this software called PySR, which I'm going to talk about today. So PySR is a tool for symbolic regression. So I'm going to kind of give background to this, motivation for it, and we're going to discuss the internals, how it works, and kind of review some of the latest features. Okay. I'm going to skip these. Okay, so I want to kind of just motivate things by sharing my interest in symbolic regression. My background is in astrophysics, and I think in all the sciences we have this issue of, machine learning is it's good at when you have interpolation, but I think in science we want extrapolation. And so there's this fundamental issue of unknown unknowns. So when you use neural networks, they are just so flexible and so powerful, they'll pick up on everything you give them. So there's this classic example that I like to show of neural networks trained to detect pneumonia in hospital patients. And it did surprisingly well, and then they found out it was just kind of like reading a token in the background of the X-ray that basically said, like, they're in this specific ward of the hospital. And so it wasn't actually looking at their lungs at all. It was just like reading the doctor's diagnosis, right? So there's this fundamental issue with machine learning and science in that you don't really know, like if you don't have an interpretation and you kind of can't build a model for it, it might not actually be learning the correct model. So I think this is kind of a massive problem for science. I think the other thing I'm interested in is that oftentimes you'll have a case where the machine learning model will kind of beat traditional scientific models. So this is an example we worked on where we predicted the instability of planetary systems, and it's more accurate than centuries of research on instability theory. And so as a scientist, I think I'm not really interested in, oh yeah, I have this black box oracle that tells me, everything. I actually want to know how it did this. Because I think if we can understand how it did this, this kind of advances our own understanding. Okay. I guess, so at the same time, there's also, I wanted to mention, there's a lot of cool interpretability techniques from the language model community. So this is a cool blog post I read recently from Anthropic on the biology of a large language model. They kind of, they interpret how language models compute addition. And it's kind of funny because they basically have like a bunch of lookup tables inside the latent space of the language model. And then they just, they look up, oh yeah, this number and this number. It kind of has like specific lookup tables for kind of every combination. So I think, I think this kind of interpretability is really exciting. But I think as scientists, I think we more so want, we want interpretability in our language, which is mathematics, right? So in science, we have this very powerful language to express our models. So I think we want to build kind of interpretations in this language. So like in physics, especially if you look at any kind of cheat sheet, Physics 101, you can see that so many physical models are just easily expressed in this symbolic language. So I think when we try to interpret machine learning models, I think it's not a bad idea to kind of use this existing language. Okay, by the way, if people have questions throughout the talk, just raise your hand up. I like interactive discussion. So yeah. Okay, so this brings me to symbolic regression, which I guess you've kind of already been introduced to a bit. So symbolic regression is a machine learning task where you are trying to find analytic expressions that fit some objective. It was popularized by John Koza in the 1990s, and then its use on science by Hod Lipson. And so rather than only fitting parameters in a fixed model, you're also now fitting the structure itself. So it's a little bit different. I like to give this plot as kind of a comparison with normal machine learning. So in blue, we have decision tree approaches. In green, we have deep learning. And in red, we have symbolic regression. And so you see that, OK, training speed, decision trees are fast. Deep learning is a little bit slower. Symbolic regression is really slow. High dimensional performance, so like how easy it is to express high dimensional models. I think deep learning is the best at this, then maybe decision trees. Symbolic regression, I mean, it kind of depends how you set up the problem, but I would say it's worse at that. And then expressivity, I think it's much worse. It kind of really restricts the space that you can model things. But the benefits you get are that if you do find a good model, it tends to be very good at generalizing, especially for physical problems. And you also get a highly interpretable model. So of course, these depend on the symbols you give the symbolic regression algorithm. If you're not using the appropriate operators, it might not give you something interpretable or that generalizes. OK. I'm going to skip some of these. Maybe we can come back to that. OK, so the tools we're going to talk about today are PySR and SymbolicRegression.jl. So these are the tools that my group works on. SymbolicRegression.jl is the kind of the back end, the workhorse. This is a high-performance symbolic regression library in Julia based on genetic algorithms. And PySR is kind of like a Python front end. Basically, I wrote it in Julia because I don't like C++. Right, that's about it. But Python is, I mean, like every major Python library, the backend is in a different language. So it just happens to be Julia. PySR is now a community project. I mean, there's tons and tons of contributors. So I barely kind of feel like it's mine anymore. So this is a list of some of them. And of course, this list is always growing. PySR is so it's flexible, user-friendly framework. A bit of the history is that, so it was kind of originated, I was using this tool called Eureka, which is this really nice library, but it became closed source and they started charging a lot of money for it. And I was using symbolic regression in my research, and it was like, you couldn't really reproduce it anymore. So I got kind of really annoyed at them, and I wrote PySR, and it's free and open source. And so the other things you get, sorry, I don't know why this is echoing. The other things you get are that it is fundamentally very flexible. Like you can hack kind of pretty much anything you want in it. So I'll show you examples of like how much you can customize it. And I think it's also kind of nowadays competitive with Eureka and speed. OK. OK, so let's kind of get into the internals a bit. So when you solve symbolic regression problems, you're trying to explore two objectives. So normal machine learning, you're just exploring accuracy. Symbolic regression, you're actually exploring two. You're trying to minimize the loss and also minimize the complexity. So it's a bit harder because of this. It makes it much harder to kind of evaluate performance because now you have this dual objective. So this is called the Pareto front, this thing right here. And let me see. OK, so how do we define complexity? In many symbolic regression algorithms, you represent an equation as a tree. OK, so this equation, y equals z plus 2 sine z, can represent as this tree. This is kind of like in a genetic algorithm context, this is kind of like the genetic code. This is like the DNA of an equation. OK, and so you can evaluate this, and it puts it on this plot where you can compare it to data. And the goal of doing this is essentially you want to search the space of all the trees until you find something that is both small, right, and also accurate. Okay, so you want to match this curve to the data. Okay, so symbolic regression is hard for many reasons, one of which is there's an infinite search space, right? There's infinitely many expressions with an infinite space of real constants. It's also a discrete optimization problem with this highly nonlinear landscape. So if you think about x times y and x divided by y, that's a single mutation, right? You just change the multiplication to a division, and it gives you a massive difference in outcome. It's also highly multimodal in that there's many different local optima. So like 2 times x, x divided by 0.5. Same loss, same complexity, but they're 2 completely different expressions in different places. So this just makes it really hard to search this space. So what people normally do is use genetic algorithms. So we'll talk about this. So if I represent an expression as a tree, I call these guys leaf nodes. And so I could have a leaf node that's a variable, I could have a leaf node that's a constant, and then the operator nodes are functions, like multiplication, sign, plus. All the operations in SymbolicRegression.jl happen depth first. So if you're doing evaluation, you kind of, you trace up here, and then you go up there, and you evaluate sign of that, and then you start from this end, and you go up there. And this is the same for like computing complexity and stuff. Okay, so when you have these expressions, you need a way of exploring this space. And as I mentioned, it's highly nonlinear. It's not kind of clear what direction to go a lot of the time. So the state-of-the-art method still is a genetic algorithm. And this pulls ideas from kind of natural evolution where you'll have mutations. So a plus, you can mutate that into a minus. Maybe a z, you mutate that into an x. You kind of make small perturbations to this expression. You can also breed expressions. So again, pulling from evolution, if you have 2 expressions which they're both okay, fits to the data, you could maybe take this subtree and this subtree and swap them, and you get these 2 children. And this kind of gives you other ways of exploring this space. So mutation and crossbreeding they're just ways of exploring this space of expressions, because there's not really you can't really do gradient descent in this space. So you can there are papers that try to kind of learn like a latent space of expressions, but it basically never generalizes because it's such a massive and nonlinear space. Like it's arguably more complex than language once you get up to like complexity 10. You just can't even model it. Yeah. Yeah. Oh, I see what you mean. So you can get, of course, derivatives of these with respect to the constants and with respect to the variables, but you can't get a derivative of a plus with respect to the space of operators. So there's not a clear direction, if you wanted to change that plus into a multiplication, it's a discrete jump. So there's not really a continuous direction. Now, of course, the constants, you can do that. And so one of the algorithms that PySR uses internally uses BFGS, and it does gradient descent on the constants. Yeah. Okay, so the actual, I just noticed, I always say like, okay, so, at the start of each slide, I gotta stop doing that. Okay, so this is a GIF of kind of what it looks like when you are evaluating, kind of exploring the space. So we see we're trying to match this prediction to the true values here by mutating that expression. So let me play this again. And you see it kind of quickly searches many different trees. It finds this one is a good match, so it does that step, mutates that node. It does explicit constant optimization. It adds a node above it. And these are all perturbations to explore this space. So essentially, the takeaway here is that this is it's a discrete optimization problem in this infinite, kind of uncountably infinite space. So genetic algorithms offer us I guess it's a slightly better way than brute force to search this space. Okay, so complexity. So when we talk about complexity, there is many different ways to define complexity. In PySR, the default is just counting the number of nodes. So if you have an equation that's just like a constant, 2.1, complexity 1. If you have this equation, sine of x times 2.1 plus y, go 1, 2, 3, 4, 5, 6. So it's complexity 6. This is the default definition in PySR. But this is completely customizable. So you could define, maybe I don't like sinusoids. I think they're kind of complex, so I want to assign them a higher complexity. Maybe there's a specific variable that you think is more complex. You could assign, this variable costs 3 instead of 1. Or you could just write your entirely separate complexity function. And if you want, so I have this 30-minute rant about complexity that I can do later if people want. I have very strong feelings about it. I think complexity is basically like a BS topic. So I have a fun rant I could give. Okay, so Pareto front, I talked about this curve of loss and complexity. So an expression is on this curve. Yeah.
Why the complexity is defined that way?
Yeah.
Many other ways it's defined.
Yeah.
Why that way?
It is the
Other than it seems very easy definition, but does it have like?
It's the simplest way to think about it. Yeah. The simplest thing for the user. But I think complexity is basically like, I'm a complexity nihilist. I don't think complexity exists. Because complexity, it depends on our understanding of concepts. And those concepts are arbitrary. So like if you take, for example, classical mechanics, we think of this as simple, like F equals ma is simple. But it required calculus to develop, right? So without calculus, it would be this insanely complex theory. So it's just like we define symbols for concepts that are useful, and that makes things simple. But I think complexity is kind of, it's impossible to pin down. And this is kind of the simplest algorithmically and to explain. But there's, this complete space of arbitrary functions. Like one of the things I tried once is I literally used the gzip algorithm. And so I ran a zip algorithm on the string, and I set that as the complexity, which would, if you have a repeat, it would kind of minimize the complexity.
Yeah, I mean, the complexity must depend on your dictionary.
Yeah.
Like you need to
I mean, basically the main thing I would say about complexity is there's not really any universal definition. I think the most useful definition is the one that you find interpretable. So if you find sine to be less interpretable than exponent, I think assigning a higher complexity makes more sense, because symbolic regression is useful for interpretability. So yeah, I mean, that also depends on the space of operators you give. So I think that's, one way to do it. I think another way is if you are using symbolic regression to find like surrogate models for like numerical algorithms, you could define complexity as the flops of each operation. That's another way. Yeah. Does that answer? Okay. Yes. Yeah. Mhm. Um, so, I mean, so symbolic regression, like genetic algorithms are dumb. They don't kind of have any intelligence at all. If you give them these features, they will find an equation in terms of those features. If you give them a feature that is kind of more physically reasonable for your problem, like the angles, they might find an easier expression. But I think the featureization is really up to the user. I mean, you might find that, oh, it keeps like mapping this variable through like an arctan. Maybe I should just give that as a feature or something. Maybe stuff like that. Yeah. 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 Well, so genetic algorithms, they can express arbitrary binary trees of operators. So it could find like sine of x plus a constant and do the offset. So, sorry? Yeah. 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 So the default loss is mean squared error. So that would punish that expression. If you're using a different, I don't know what would give the, I don't know, like if you have some kind of, like a earth mover's loss or something, like maybe that would help with that problem. I don't know. Like this, yeah. I mean, but the default is just mean squared error. So if the sinusoid is offset, it would be a bad loss. Yeah. 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 Thanks. Okay. Were there any other questions? So the Pareto frontier is essentially, wait, I don't have a diagram. It is a set of expressions that dominate all other expressions. So an expression A dominates B if A is both simpler and more accurate than B. So another way to think about this is the Pareto frontier is a list of expressions that kind of are the most accurate at that complexity. So there's no expressions that are both simpler and more accurate. This is the Pareto front. Okay, so in the PySR SymbolicRegression.jl context, there is this concept you will see, so you'll see it when it gets printed out. It's called the Hall of Fame. This essentially is it tracks the best expression at each complexity. So this preserves all the discoveries throughout the search. So if it kind of evolved this expression and then that expression like died out, it would still preserve that. It would still have this recorded. Oh, this is the best expression I saw at this complexity. So there's no forgetting good expressions, and this is what's used to form the final Pareto front. Okay, so the way this search actually works looks like this. It's this big loop that basically just runs like a million times. You have this population of expressions. You could think of this as like a population of organisms. Each expression is an individual organism. And what you do, maybe you have 100 expressions. You pick some from the population. Maybe you pick two. You pick two random expressions. Take those random expressions. You pick the fittest one. So fitness might be defined as the loss plus a constant times complexity. It might literally just be loss. You could define an arbitrary fitness if you want, but it's basically the accuracy of the expression. You take the fittest of that subsample and you perform some perturbation to it. Maybe you mutate it. Maybe you change the y into y squared. Maybe you delete that part of the expression. Maybe you do a crossover, so you kind of blend parts of them. Maybe you do an algebraic simplification, or maybe you even do a constant optimization with gradient descent. Maybe do like 10 steps of BFGS or something. So these all serve as kind of ways of exploring this discrete search space. You do that, you get a new expression out, and you stick this back into your population, and you kill the oldest one. So the traditional way of solving this is in tournament selection is you would kill the weakest expression. This tends to kind of converge too quickly, and it would converge prematurely and kind of find like a local optima. So this is called age regularization, where you kind of kill off the oldest member. Okay, but it's not living, so don't feel bad. Okay, so the algorithm itself looks like this in kind of pseudocode. So what we do is we have this kind of annealing that happens where you'll have a population, you'll do this loop maybe 1,000 times. You kind of mutate expressions, replace them, mutate, replace, mutate, replace. You do this many, many, many times. And this temperature parameter is kind of like a annealing, so that when the temperature is high, it's more likely to accept changes. And as the temperature gets lower, it only accepts changes if the loss is better or something. But otherwise, it just rejects the change. Okay, so this is kind of the core evolution that takes place. Then we run this simplification, kind of trim the trees down, and the final stage is we run this actual optimization. So we run constant optimization to kind of clean up all the constants. Okay, and this loop just happens, many, many times. So it's kind of like a dumb algorithm. Like I don't think it's that sophisticated. And genetic algorithms have been kind of the state of the art for this problem for a long time. And kind of all the innovations have just been like little tricks to prevent premature convergence or like, just speed it up. The other thing PySR does is that to take advantage of like very distributed systems, it splits up populations to cores. So if you have 1,000 cores, maybe you set up like 1,000 independent populations, and they evolve independently. And what happens is after some number of steps, there'll be this migration period. So a lot of it's just borrowing from evolution. So you'll actually have the best expressions from this population migrate to this one. The best ones from this one migrate over there, and they kind of share their like genetic traits, if you will. And this all happens asynchronously. So this is kind of a way of taking advantage of highly distributed systems. Okay. Any questions? Yeah.
Like you mentioned, these genetic algorithms are essentially like they're like a sophisticated version of
Yeah.
so is there some like mathematical framework, or is it, do you think that we are just like lacking the mathematical framework to like rigorously describe what's going on beyond the mechanics of your, let's say, GA algorithm you have to design? Like, is there like some mathematical framework you can embed?
To do a search, you mean, like a direct search?
People say that it's heuristics, it's meta-heuristics, it's evolution inspired, but then like mathematicians say that, yeah, we can't really guarantee if any, like convergence
Yeah.
or like.
Yeah, even with crossbreeding, it's non-convergent. Yeah.
So do you think it's that it's like lacking the mathematical framework, or it's just because there is no conventional mathematics to describe?
Yeah, I mean, I guess those are kind of the same problem in a way, right? Like I think, yeah, we don't really have a good way of describing why it works. You can empirically measure like, oh yeah, it is like, 14 orders of magnitude faster than brute force for this problem. Like you can actually just empirically measure that. But we don't really have a way of, I guess, describing mathematically the search space that genetic algorithms explore better. Yeah. I mean, I think it's definitely a problem. I don't think I'm smart enough to solve it. I hope someone does solve it. Yeah. Is there another? Yeah. So there is a deterministic parameter that you can set to true. It only works in serial mode with a single core. If you have multiple cores, it's non-deterministic because it kind of evolves asynchronously. So if one population just finishes earlier than the other, it will return earlier. So the determinism only works for one core. No, because the CPU scheduler is non-deterministic. I mean, we could do some kind of like locking to fix the order, but I guess we just haven't added it yet. But I guess you could. But it might just be much slower. I don't know. Yeah. Yeah. So it's highly problem dependent. I think it depends on what your use case is. If you're using it to interpret something, that is completely up to you and kind of what complexity you're comfortable with. And it also depends on, does it look like existing models that I already have? And then I can just like, oh yeah, this piece I already understand. This extra piece is new. So then you could, accommodate like a larger complexity. So I think it's just highly problem dependent. I think what was the second question? Oh, so there's a heuristic that everybody kind of uses. So when you get this, let me see. So if I have this complexity and this loss, what you'll usually have is something like this. And normally what people do, this is complete heuristic. There's no like rigorous way to do this, is you look for the biggest drop as a function of like complexity. So this is the highest derivative along the Pareto frontier, and this is probably best, question mark. I mean, it's complete heuristic. There's no theory behind it. It works sometimes. Yeah, there's not really like a good way to do this. I mean, sometimes you might want to have multiple expressions and kind of use the simpler expressions to bootstrap your own understanding of the more complex ones. So like, oh yeah, this is like the first order form, and now I understand it. And then this is like the second order, the higher order contributions. So you can kind of use multiple expressions too. Okay. Cool. I'm going to skip some of these. Okay. Oh yeah, maybe let's take a break actually. Let's do like a 5-minute break so people can, I don't know, take a breather.